In this discussion, we shall talk about different representations in quantum mechanics, and it is almost obvious to you that the physical observables would not depend upon the representation that we are using, rather should be independent of the representation. So, the expectation values of operators which denote physical observables should remain same. However, it is possible to go from one representation to another. In particular, we are talking about the coordinate representation or the position representation and the momentum representation, and we will see that how they are connected, or rather what is the form of an operator in momentum representation and coordinate representation. And to begin with, let us talk about the x operator. So, we start with position representation. And x coordinate of a particle is associated with the operator x. So, we will write an operator with a hat, and so it is associated with x, and where of course, my x variable that goes from minus infinity to plus infinity. So, the ket x, so this denote a particle at x such that x cap acting on this ket will give me the position and will return me back the ket. And of course, your x cap is a Hermitian operator which will come, and so if a particle is in some state psi is an arbitrary state, the amplitude of the particle, this is important, the amplitude to find a particle at x is the complex number x psi, and so basically the functional dependence of this number of this number on x is what we call as wave function psi x. So, let us see. So, the definition of psi of x is the overlap with x and the arbitrary state psi. So, since the basic postulate says that the total probability of finding the particle should be 1 between minus infinity to plus infinity. So, we can write this as minus infinity to plus infinity mod psi x square is equal to 1, and that is equal to minus infinity to plus infinity, and you have a dx, and then there is a psi x psi, and so that is the definition. And now, let us calculate x and x cap psi. So, that tells that this is x cap star and x psi. Now, x is equal to x cap star. This is called as the Hermitian operator. X has to be a Hermitian operator because x is related to the measurement of the position of the particle. So, it is a physical observable and hence the operator should be Hermitian. So, if this is true, then this x cap psi is same as x cap x psi, which is same as x psi and nothing but x psi x. So, this is the so x cap operator being taken between these states x, which we know that x acting on x cap acting on x will give me x and will return the ket x. And so, that is now taken with this with an arbitrary state psi, and it gives me the position of the particle x and returns me the wave function which is a function of x. So, if you want to do the same calculation in continuum notation. So, this is in discrete notation where we have extensively used the Dirac's Bryan-Ket formalism. If you want to do it in so let us write it in continuum notation. It is the same thing excepting that we are writing it in continuum notation now. So, it is this and this is minus infinity to plus infinity dx and x cap and x prime, and so this is psi. So, we have simply introduced states completeness of states, and this is nothing but minus infinity to infinity dx and x cap x prime and a psi of x prime, and this is nothing but minus infinity to plus infinity dx x prime delta x minus x prime and a psi of x prime, which is nothing by using the property of the delta function, it is nothing but x psi x. So, it is the same thing that we have gotten here and here we have used two different notations in order to arrive at the same result. All right. So, we are dealing with the position representation, and let us now talk about the momentum operator. So, the momentum operator is written with a p cap, and the definition we can prove this, but however, we will skip the proof and take it as a definition. So, definition is that a p is written as a minus I h cross del x. So, we may actually define a p and a psi of x to be a state, a momentum eigenstate, let us call it as u p x, where p this subscript denote the momentum, and similarly as earlier. So, it acts on a ket p and returns back the momentum of the particle and the ket itself, and so this is nothing but then minus I h cross del x of u p x, which is equal to p u p x. And similarly, when we want to write the expectation of the momentum operator between the position ket x and an arbitrary state psi, this is nothing but minus I h cross del psi del x. And so, this if you want to contrast with what we have just obtained in the last slide, this is equal to x psi x. So, as I told you that it is possible to prove the definition of the momentum operator. However, we will skip that. Rather, what we would do is that we will go ahead to prove the form of the position operator in the momentum space. And in order to do that, let us the question is find x cap in the momentum representation. Okay. And to do that, let us take an arbitrary an arbitrary state psi, and we can use the commutation relation between x and p to be. So, remember x and p, the commutation is equal to I h cross I, where this is an identity operator, or you can call it an identity matrix, and basically the x and p, which are the conjugate variables here, they do not commute, and the commutation give rise to a finite quantity which is equal to I h cross. And remember that they both are infinite dimensional matrices, each of x and p, and infinite dimensional matrices do not commute. So, now I can write, or rather take this commutation relation between the ket p and psi, and this is nothing but equal to p x cap p cap minus p cap x cap and a psi, and which is nothing but equal to, if I separate it out, it is x cap p cap psi and minus p p cap x cap psi, that is separating it out. Now, we have p x cap p cap, I leave this first term as it is, and apply, or rather operate p cap on the bra p, which gives me a p, and so this is equal to a x cap and a psi. So, this is also again taken as momentum is also a Hermitian operator, which means a p equal to p star. Now, if I write this as equation 1, if I rearrange equation 1 and use the commutation relation, then I can write this as a p x p x psi equal to a p x p psi and a minus I h cross p psi. That is just rearranging this and using the commutation relation. And now, take the first term. So, let us call this as 2, take first term in the right RHS of equation 2, that is this term, and this term can be written as p x cap p cap psi, which we use our continuum notation, which is equal to p x cap x again use the completeness of states, and this is nothing but this is equal to a dx x exponential I p x by h cross and a minus I h cross d dx of psi x. Now, I leave one step for you to figure out and complete. So, using integration by parts, please look at calculus book and or rather mathematical physics book and see what integration by parts is. And this can be written as, so this same term I write it here, this is equal to a I h cross a dx and a d dx of x exponential I p x by h cross psi x. So, this can be written as I h cross d dx of exponential I p x by h cross psi of x plus I h cross dx x I p over h cross exponential I p x by h cross psi of x. If you do it carefully, you will get it. So, this is nothing but this is equal to the Fourier transform of psi of x, which is nothing but psi of p. So, this is psi of p and this is I h cross p and a d d p of dx exponential I p x by h cross psi of x. So, this whole thing is written as d d p of this and one can check that that is true. It is I h cross psi p plus I h cross p d d p of psi of p. Okay. So, this is equal to where of course, we have used definitions such as let us see the definitions being used. We have x p psi which is equal to minus I h cross d dx of psi of x, which is known, and x of psi is equal to psi of x and p of psi is equal to psi of p. So, this is our that first term on the RHS of 2. If we put it back, we will get putting it back in 2, we will get a p so, we will get a p and a p x psi, and this is equal to I h cross psi p plus I h cross p d d p of psi p and a minus I h cross p psi, and this is nothing but psi p. And so, there is a plus I h cross psi p and there is a minus I h cross psi p, they would cancel, and I am going to also lose this p because p is not equal to 0. So, they can be divided by in both sides, and then finally, I land up with a p x cap and a psi which is equal to a I h cross d d p of psi p. So, that is the definition. So, if we want to get the operator x cap in terms of the momentum, so we will knock off the end states and we will get x cap equal to I h cross d d p. So, that is the definition of position operator in the momentum space. As I told you earlier that you are aware of and very familiar with the momentum operator in position space. However, there is an alternate description possible in quantum mechanics where we do not talk about position representation, but we talk about momentum representation, and a position operator takes a form of this kind in the momentum space, whereas the momentum operator in the position space has a minus sign with a del ddx or del x as you wish to write. So, this is the position operator. Of course, this p is in the x direction, here is a canonical variable in the x direction corresponding to the x motion. So, let us write down that how would it be. So, any operator can be written down in any representation however, the expectation value which corresponds to physical quantities remains conserved. Let us write an operator O in momentum space So, O is written in OP. So, the expectation value of OP is equal to psi star P OP psi P dP. Psi P, if psi of P equal to delta of P prime minus P, then of course, your OP is equal to a delta P prime minus P OP delta P prime minus P and a dP, which gives me nothing but OP prime. Sometimes it is important to find powers of the position operator. So, let us take x to the power n. So, x to the power n expectation is written as psi star x x to the power n psi x dx, which is equal to psi star x dx, and there is a 1 over root over 2 pi h cross and a psi p x to the power n exponential I p x by h cross dp, and hence x to the power n or rather this one exponential I p x by h can be written as minus I h cross d d p whole to the power n exponential I p x by h cross. See, every time you take a derivative of this exponential function which is oscillatory, you would get x here. So, if you take it n times, you will get x to the power n, and that is what it is. So, your x to the power n is nothing but I h cross d d p of n. So, this is the, so if you raise x n times, the operator has to be multiplied that many times in order to get it in the momentum space. Let us give a simple example. So, Hamiltonian of a quantum harmonic oscillator. So, this is equal to H equal to p square over 2 m plus half m omega square and then x square. So, I can write x square as I h cross d d p square, which is equal to p square over 2 m minus half m omega square h cross square and d 2 d p 2. So, this is the form of the Hamiltonian in the momentum space, and we have to solve a potential or rather a Schrodinger equation with this Hamiltonian. We have always solved the quantum harmonic oscillator problem, writing it in position space, that is changing the p to minus I h cross del del x, and then I have gone ahead and solved the Schrodinger equation. However, an alternate thing can also be done in the form of this. Let us go to another important discussion, which is called as density operators and density matrices. So, the origin of the problem is like this, that usually we deal with a large number of particles when we talk about a particular experiment, or even talk about the Young's double slit experiment. We do not talk about a single photon, we talk about a large number of photons. So, there is a statistical analysis, or the statistical theory has to be inbuilt. Now, the statistical probability or the weightage that is associated with the statistical ensembles, that has to be taken into account, and as well as the probabilistic interpretation of quantum mechanics has to be taken into account. So, the problem as in classical statistical mechanics, which was only the probabilistic interpretation, or the probability was coming as a weights of the statistical the entities, is no longer true. We also have a quantum mechanical probabilistic interpretation which comes and interferes with that. So, in order to develop the quantum statistical mechanics, it is important to study these density operators or the density matrices, and will give you the important points, and probably do one or two examples with that. Most of the time, or okay, I mean, which is true as well. You can say that there are exceptions to this as well. So, most of the time we worry about, we start from a given state of the system, and then allow the system to evolve. However, there are exceptions where the initial state is not completely known, we will say it in a little technical words, we will say that that is not pure and may contain admixture of states. So, this an example can be given as the polarization state of natural light. What we mean by is not laser, it is basically natural light is not known with precision, with certainty, which means that there are different polarizations that are mixed. For sure, we know that the amplitude is actually could be in any direction, and this is called as a polarization being not in a given direction or it is not known. And then in this particular case, that system is said to be in an admixture of states with probabilities P1, P2, etc., such that sum over I P I is equal to 1. So, what I mean to say is that the probabilities intervene at different levels the initial information about the system ballistic. So, it becomes probabilistic, and the final states, that is the time evolved states, also suffer from probabilistic predictions. So, we will talk about density operators, but while we talk about these probabilistic interpretation, one thing that comes to my mind is that sometimes the students get quite confused with the fact that we write. So, this is just a discussion which is slightly out of the way, but it is important nevertheless. The discussion is that we write a total state psi and write it in terms of C n and a phi n, where C n's are, they depend on time, whereas the basis states phi n's are constants. So, phi n is a basis that spans the Hilbert space. So, it is often said that the probability to find the state in phi 1 is associated with C 1 square and phi 2 is associated with C 2 square and so on. But this statement is not correct, because the correct statement would be the probability to find the eigenfunction or rather to find an eigenvalue corresponding to phi 1. So, the correct statement is the probability of finding eigenvalue associated with phi k is C k square, because you have to allow for, because if you say that the probability that the state is found in phi 1 is C 1 mod square, phi 2 is C 2 mod square, that defeats the purpose of quantum mechanics, because there has to be necessarily interference between these states. So, those interference terms such as a C k star and a C k prime, interference terms should be present. So, just to reiterate this, when you write a total wave function as a sum of these amplitudes and the basis states, there is a sum over n. So, it is not true. So, this is false, or rather this is untrue, that the probability of finding the particle in phi 1 is C 1 mod square and phi 2 C 2 mod square and so on. Rather the correct thing is that the probability of finding the eigenvalue associated with phi 1 is C 1 square, C 1 mod square and C 2 mod square and so on, because then that allows for the cross terms or the interference terms to be present, which are very important for quantum mechanics. Anyway, we will come back to this density operators and see that what they or density matrices, what they see, what they actually mean. So, to study statistical mixture of states, we should rather introduce a density operator which permits a simple description of the statistical admixture of states but also there is another advantage of using the density operator, that is without using the state vector or the wave function psi, everything could be done in terms of the density operator. So, we shall show that characterizing a system by its state vector is completely equivalent to characterizing it by a certain operator acting on the state space. So, that underscores the utility of the density operator, that we can actually do away with using the state space and completely work with the density operator. So, let me box this rather important statement which we are going to prove. So, recall that psi equal to sum over n C n t u n, and for any operator A, we can write it O also, previously we have written it O, but it is just the same thing. So, the matrix elements between two basis states u n is given by this. So, the expectation value at a time t is A t, its psi t A psi t, this is equal to n and p. So, this is C n t C p t A n p, where A n p is defined earlier. Now, so the expectation value A t involves these quantities C n star t C p t, which are the amplitudes, the complex amplitudes. But see that these amplitudes, these product of amplitudes are the matrix elements of an operator psi t and psi t. So, this is the projector onto the ket psi t. Well, let us see how. So, let us take an operator, say let us call this as B, which is equal to, will of course soon change its nomenclature from being B to rho. So, this is equal to its psi of t. So, this tells you that B acting on psi t, it is equal to psi t and psi t and psi t and so on. And so, this is nothing but a C n star t and C p t and a psi t and so on. So, this is the matrix element, or rather the eigenvalue of this operator. So, this B acting on psi t will give me this. So, it is now natural to introduce density operator rho of t, where rho of t is exactly what we said about B, that is rho of t is equal to this projector psi t and so on. So, in the basis, so psi's are written in the basis this un. UNs are assumed to be orthonormal basis, but it is not a big problem if they are not. There are always going from non-orthonormal basis to orthonormal basis by doing a transformation called as the this Gram-Schmidt orthogonalization. And so, this is so the matrix elements of the operator are, so rho m n t equal to u m rho t u n, which is equal to C m star t C n t. So, now rho t yields all the physical observables, as was the claim that it will replace the usage of the state vector psi of t. So, before we show that, this is so your sum over n C n t mod square, it is equal to rho n n t, which is equal to trace of rho t, which is equal to 1. So, this talks about the conservation of probability . So, the expectation value of any arbitrary operator is written as u p rho t and a u n a and a u p, and this is nothing but summation over p u p rho t a and u p this, and this is nothing but trace of rho t a. So, we do not so we simply have to calculate the density matrix, multiply it by the operator and take the trace, that will give the expectation value of the operator. So, this is completely equivalent, and the last thing that we can see is that the equation of motion d dt of rho t, it is equal to d dt of psi t and a psi t outside. Now, keeping that psi t and a psi t taking the derivative on the other psi t. So, this is equal to minus I by h cross h t psi t psi t, and this is a plus I by h cross psi t psi t h t, and this is nothing but minus I by h cross h t and rho t. And so, this tells that the equation of motion of the density matrix of the density operator is the commutation of the operator with the Hamiltonian. So, if these two commute, then they have same state of eigenstates, or they have the same basis, they can be diagonalized in the same basis. So, for pure states, we have defined pure earlier, it means that the initial state with which we begin with is completely known. So, there is no statistical admixture at all, and so for pure states rho dagger of t equal to rho of t, rho square of t equal to rho of t, and trace of rho square of t equal to 1. And as I told that if there is an admixture of states, some of these properties do not hold good. We will see for a particular example.